You don't like that right after spring break? Good morning, everybody. Welcome to lecture. Hope you had a nice spring break. What's that? Until now, right? Until now. Welcome back to reality. Doesn't make it any better that it's so dark out there this morning. Just a quick reminder, there is an exam coming up on Friday. It's going to cover the little bit of chapter 4 that we didn't get to on our first exam. Excuse me, as well as chapters 4 and 5 and 6 rather. Only the sections, of course, that we covered in class. So check back to your notes for that exact coverage. It'll be in class again. The format will be similar to the first exam, where we have about 4, maybe 5 written problems. Again, you're welcome to bring a calculator. I would encourage you to bring a calculator and one 8.5 by 11 sheet of notes, if you would like. Front and back's good. Any tables you need will be provided. And then I'm going to do a few extra office hours this week to help if you guys need to come by for any additional questions. I will have my usually scheduled office hours as well, Monday and Wednesday. Those are the same. But I'll also do these extra hours on Tuesday and Thursday. I'll send an email around to the class with these details, just to make you aware of these. And they will be in my office, in my office, Cock and Salt 304, not the tutor room. So Monday, Wednesday will still be in the tutor room. These extra ones will be in my office, not the tutor room. Any questions or comments about the exam? I'll have your homework 5, whatever the one you turned in right before break. I'll have that back to you guys on Wednesday. FYI.
Are you going to post solutions to the review exam?
Solutions to the review exam. I think they are. I think there is solutions posted. Yeah, I think I put those up over break. I'll double check that though. Those should be up there. No questions? All right, let's go to Happy St. Patrick's Day, everybody. See, a few of us have green on at least. I think I failed to do that today. Anyway, we're going to forge ahead here with Chapter 7, confidence intervals. Just a quick review here from what we talked about. We introduced this last Friday, a week ago now. So if thinking sort of big picture here, back to Chapter 6, we were talking about point estimation, and our goal there was to find a single number that in some sense gives us a good estimate for whatever the parameter is that we're interested in. So as far as some sense, a good estimate, that was things like finding an unbiased estimator or one that has small mean squared error, small MSE, some of those kind of things. And we talked about a few methods for doing that, the method of moments. We also had maximum likelihood estimation. But the kind of the problem moving forward here is that if I just give you a single number, that's not telling you really how precise that estimate is. So if I just give you one number, that's good to get a kind of a ballpark figure, but it would be good if we could give some estimate of how precise that guess is. So instead of guessing just a single number, giving just a single estimate about our population parameter, can we somehow determine a range of values that would be good for that? And so this leads us to this idea of a confidence interval. So kind of our motivating example here, which we'll move past today, but if we start out with a normal random sample from a normal population, where we're trying to estimate the mean, so we don't know what the mean mu is. For now, we're saying we know what sigma squared is. Then our confidence interval is given by this thing here, and so this form here is going to be sort of our general. What this is here. This is an estimate, and then we're going to add and subtract some margin of error. So for this sort of simple motivating case so far, our estimate here is the sample mean. Again, we're trying to estimate the population mean here, so we're going to estimate that using the sample mean. We saw back in Chapter 6 that that's the maximum likelihood estimate. I think it's also the method of moments estimator here. And then we're going to add and subtract something, right? We're going to add and subtract some margin of error that's going to give us that kind of that range of values, or that kind of telling us how precise, that measure of precision. The margin of error telling us how close we might expect that guess to be to the true value. So here the general form of these confidence intervals in this class anyway will always be whatever our estimate is, and then we're going to add and subtract a margin of error to give us this confidence interval. Okay, so the only other weird notation up here maybe is this z sub alpha over 2. And that's, again, remember, that's called our critical value, and that's just here the definition. It's the value on the standard normal, so we're using z here, that has probability of alpha divided by 2 above it. So alpha was called our significance level, and that kind of corresponds to our confidence level. So if we want, however confident we want to be in our estimate, we're going to use a particular critical value for that. And then just a quick reminder before we look at critical values one more time, that when we interpret a confidence interval, we had a discussion about this on Friday, where a confidence level is telling us about the success rate. So it's not a probability statement. It's telling us how sort of in the long run, if we repeated this experiment over and over, sort of how often we would catch the true value in that confidence interval. So we'll say something like we are 95% confident that, and then we'll give our interpretation. So just remind you that we're talking about a success rate here. And then quickly to remind you of this confidence level idea. Again, we want a range of values. So we're taking our estimate plus or minus something, and depending on the confidence level, that will tell us how to find our critical value. So sort of our usual, sort of our common confidence levels here, the most common ones are 90%, 95%, and 99%, which corresponds to alpha of 0.1, 0.05, and 0.01. And then there, kind of, this picture, we looked at this on Friday, kind of showing you where those numbers are coming from. My critical value, z sub alpha over 2, this number right here, that means that there is alpha over 2, or 0.05 probability of being bigger than 1.645. So if there's 90% in between plus and minus 1.645, I have 10% outside those numbers. So these are some numbers that you'll get used to seeing. That's usually, I'll ask you to give me a 90% confidence interval or a 99% confidence interval, something like that. But in general, you could find, I could ask you for an 83% confidence interval or a 52% confidence interval. The general way of doing that is if I want a confidence level of C%, so whatever that is, then I just need to figure out the area that's outside of that and divide it by 2. So for example, if this is my Z, here's 0. If I want C% here in the middle, well, we know the whole curve has 100% area, or an area of 1. So if I can find alpha, so take 1 minus C over 100, then this area here, I want to find this number here such that this area is alpha divided by 2. So whatever confidence level I ask you for, be it something other than 90, 95, or 99, kind of this is your way of figuring out exactly what that is. So if I want, let's say, if I wanted an 82% confidence interval, I don't know why I would ask you for that, then you would want the area up here to be, what would I want that upper tailed area to be? 9%, right? So I would want 9% or 0.9 area up there, and then same down here. So that's the way you would go about finding these, and then I just need to find what that z value is for that, and I'll do that using the table, just kind of like we've done a number of times now. Okay. Okay, yeah, so just kind of think about where we are so far. Sort of this is our motivating example. We've found ways to give 95 or actually any % confidence interval for the population mu. So again, we're trying to estimate the population mean here, remember? And our setup here so far is that we have a random sample, IID, normal random variables, and we know what sigma squared is. So why is this again? This is good to motivate, kind of thinking about how we can set this up. But there's two reasons this is not all that helpful. Does anybody, I sort of mentioned these last time we were in here. Does anybody have any problems with these assumptions that we're making here? Say that one more time. Okay, so the response was we have to know both mu and sigma squared. Again, we're not saying that we know what mu is at this point. We could set this up such that we can. We're trying to estimate mu here, so we're still not saying we know what mu is. If we knew what the population mean was, we'd be done, right? If I know the population mean is 20, then we're all set. But you are exactly right. We're saying here that we know what sigma squared is. So the setup here is that we don't know mu, but we do know sigma squared, and that's very, very unrealistic. I guess sometimes in manufacturing you can sometimes control how precise your machinery is, but maybe not know what the mean is. So maybe in there it would possibly hold, but in general this is a very limiting assumption. And then the one other sort of very limiting thing we're talking about here. Does anybody? I think Stephen, you said it. Anybody else see another problem here? Yes.
Do we need to know the data?
Yes. So what do we need to know about the data?
We need to know the points.
Well, yeah. Okay. So you're saying we haven't actually collected the data yet? Is that what you mean?
Yeah, I guess.
Yeah. Right. So we're assuming now that we haven't collected the data, but that we will collect the data. So that's something we'll get to, I guess. But what am I assuming about the data, I guess here? Yeah, that's right. So I'm saying that it's a normal, that it's a random sample from a normal distribution. So from a normal distribution, and as we've seen before, not everything follows a normal distribution, right? There's lots of things that probably don't follow a normal distribution. Things that are skewed, like income or house prices. Go back to our discrete random variables, right? A binomial random variable is not a normal distribution. The Poisson is not a normal. I mean, all these things we've talked about, all these different distributions that are not normal. So what do we do? What do we do for in that situation? So this is also unrealistic for a general setting. So sometimes it might be okay to assume your data follows a normal distribution, but other times it might not be. So we need to kind of deal with both of these issues in order to have something that's more useful in sort of a practical sense. Okay, so that I think that brings us back up to where we were last Friday. I think we're now middle of page 5 on your chapter 7 notes, moving into section 7.2 and 7.3. Okay, so thinking about how we can sort of start to work on both of these issues that we had just on that previous slide. So again, kind of we'll address that first one. So suppose we still have a normal distribution, but now let's think about what we can do if sigma squared is unknown. But what we've seen before is that if I have a random sample from a normal distribution, again, not worrying about the parameters at this point. We know that the sample mean x bar follows a normal distribution, mean mu, variance, sigma squared over n. Nothing new. Again, we can standardize and get to something that follows a standard normal distribution. So this is our z. We take x bar minus mu divided by the standard deviation. So now we can think about what to do if we don't know what the population standard deviation is. So any ideas you guys think about what are we going to do if we don't know what the population standard deviation is?
You have to solve for it, right?
Solve for it? So what do you mean by solve for it? You mean in that formula right there?
Yeah, I guess.
Yeah. So you mean solve this thing right there. So the problem is that from that formula we don't know what mu is, and now we're also saying what if I also don't know what sigma squared is. So what are we doing? So think about what we did in chapter 6. I don't know what the population mean mu is. So what am I going to do about that? Estimate it. Yeah, exactly. So that's I don't know what the population mean is, so let's try to estimate that. Similarly, if I don't know what the standard deviation is, let's go about estimating that too. So we can do same exact thing as we're kind of doing all along here. So the idea here is that I can use my sample standard deviation to estimate the population standard deviation sigma. So if you remember the population variance, S squared was 1 over n minus 1 times the sum that was my population variance, or sorry, sample variance. So my sample standard deviation is just the square root of that thing. So yeah, that's sort of the very natural thing to do. So if I don't know what sigma is, well, I can just estimate it using my data. Again, and the sample variance is something we're sort of thinking about. Maybe we haven't collected data yet, but once I have collected data, then I can calculate exactly what that is. So that's great. The small problem here is that if I go from x bar minus mu over sigma over the square root of n, this thing is normal. This is distributed as normal 0, 1. But unfortunately, x bar minus mu divided by s over the square root of n is not normal. So if I do know the standard deviation sigma, then I have something that's normal. If I don't, then I have something that's not normally distributed. So what are we going to do here? So this leads us to a new distribution to talk about. And this is something called the t distribution, or student's t distribution. We'll mostly just call it the t distribution. So again, when I have the same setup kind of as before, if I have x bar being the mean of my random sample size n from a normal population with mean mu, but I don't know again what sigma is, then this random variable, so dividing by s instead of sigma, follows something called a t distribution, and has one extra parameter, which is the degrees of freedom. So we'll say what that is a little bit more here shortly. So again, when I plug in the sample variance, the sample standard deviation instead of the population standard deviation, I get something that's not normal, but something that instead follows this t distribution. So just some quick properties about this t distribution. If you there in the middle of page 6 on your notes, you can see there's some pictures there, which we'll look at on the next slide here. So this thing is not normal, but it's close to being normal. So it's kind of has some properties that we like to that we've used from the normal distribution. It's unimodal, it's symmetric, it has mean 0, and it has slightly heavier tails. So the tails are going to be slightly fatter than the normal distribution. But as the degrees of freedom, so here this is the degrees of freedom. So as the degrees of freedom gets bigger and bigger, the t distribution becomes closer and closer to the normal distribution. But to show you some pictures here, so when I have when my degrees of freedom are smaller, so when v is just 1, for example, or nu, I guess that is, and when nu gets larger, you can see that this thing gets closer to the normal curve, which is the black line there. So just being very, we can solve exactly what this distribution is, and we know that it's a t distribution, which is very, very close to something that looks like a normal distribution. So again, notice that it's centered at 0. It's unimodal. It's symmetric. Those are same as the normal distribution that we've looked at before. Okay. Questions or comments so far? Okay, so this is sort of well, yeah. So one more definition, I guess, for us here. Just like we had a critical value for the standard normal distribution, our z sub alpha, we have a critical value for our t distribution here as well. Now it depends on more than just alpha. It also depends on the degrees of freedom. So whatever the degrees of freedom are, that will determine what your critical value is. But same setup. It's going to give us the area above that value is alpha, or whatever the number that we have down there. So that's going to be our critical value, which we will use in our confidence interval as well. Okay, so this has kind of allowed us to address that first issue. So again, remember, if I don't know what the sort of in a more realistic setting, I don't know what the population standard deviation sigma is. So what I can do is I can just estimate that with the sample standard deviation, and that just gives a slight change in our formula for the confidence interval. So now, supposing that I have collected data and I can calculate the mean, the sample mean x bar and the sample standard deviation s. Again, as long as I still have a normal population, we're still looking at that. Then my confidence interval will look like this. So this is, again, write this in different form. This is x bar plus or minus t sub alpha divided by 2 with n minus 1 degrees of freedom. I'm going to multiply that times s divided by the square root of n. This is my critical value. And then I'm plugging in s instead of sigma up over here. So again, it's same formula as before, right? I have my estimate, sample mean x bar, and then I'm adding and subtracting something. And because this thing doesn't have a normal distribution anymore, I have to change what that something is, but it looks the same. It's critical value times standard deviation of some sort. Again, something we won't talk about as much, but if I want just a confidence bound, so if I want just an upper limit or just a lower limit, I can find that exactly like we did before. Those will give me upper confidence bounds and lower confidence bounds. Okay, so why does this thing? Let's do a little derivation here. Why is this confidence interval? Why does this give me what I want? Okay, so again, what we have here is that x bar minus mu divided by this sample standard deviation s over square root of n. We're saying this thing is distributed as a t distribution with n minus 1 degrees of freedom, and I want to find two numbers, let's say c and d, such that the probability that when I have a random variable x bar in there, I want this to be equal to 1 minus alpha. So 95% maybe, or 99%, or whatever it is there. Okay, so again, because I have this t distribution, it's not a normal distribution, but it has the same sort of properties. So this is the same as finding the area such that outside of those numbers is just alpha. So that would be the probability that x bar minus mu being greater than c is the same as, change that, less than or equals to c. Being greater than d. So if I want the area between c and d to be 1 minus alpha, I need the area outside of that to be alpha. And again, if I have two parts, I'm splitting this into two tails. I need each of these things to be equal to alpha over 2. So that's just again saying I want to find, let me change colors here. if I have my t distribution here, so this is my t. Again, it's centered at 0. Again, I want to find c and d here, such that the area in here is 1 minus alpha. That means I need both tails to be alpha over 2. And so that's kind of exactly the definition of my critical value. So then I'll just have d be this critical value of t sub alpha over 2 with n minus 1 degrees of freedom, and c will equal negative d. So again, we're going to have kind of that plus or minus, same type of thing as we had going on before. I can write all this out in terms of probability statements, but I think I'll forego that for now. But again, because we know what the distribution of x bar minus mu over s over the square root of n, then this is exactly kind of how we found this before. We just have a t distribution now instead of the standard normal distribution. So if I want a symmetric interval here, I can just do a plus or minus with the same critical value as we found before. Okay, so how do we actually go about finding these critical values? Suppose that my sample size is 5, so I have a very small sample, and I want to know when alpha is 0.05. Again, my t distribution here, this is a t distribution with n minus 1, so 5 minus 1 degrees of freedom, or 4. And I want to know what these numbers are here, such that the area outside of that each is alpha over 2. So this is, or 0.025. So is that over here? Okay, so this is where we're going to introduce a new table. So if this was a normal distribution, again, we've done this a number of times. You'd find the probability in the table. You'd find what the z-score was, and there you'd have it. We have a new table to look at. I think I have the table. Did I not put that in the notes here? Well, that's unfortunate. Yeah, so there's one on page 8 of your notes. So I was hoping to actually show you that, but we can just ask you to look at your notes. So what we do is we find in table A5, A.5, I guess. The first column says new, and this is our degrees of freedom. And so you want to just trace down that, find in that column. So this table is similar to, but a little bit different than the other table. You want to find what your degrees of freedom are. So here are the degrees of freedom. Again, it's always n minus 1, so that's 4 here. So you trace down to the 4 row here. And then we want to find what the tail probability kind of being above that is. So I think if you go over to the third column, that'll give you 0.025, and you can see there that is I think what is here. This is 0.10, 0.05, 0.025, and you'll find the number right here is 2.776. Okay, so that tells me that this number down here is, this thing here is 776. And this thing down here is negative 2.776. Okay. So you can use the table to find your critical values here. We'll do a few more examples of this. But again, our notation here, let me just write this out formally. This here is a critical value t with area 0.025 above it, and my degrees of freedom are 4. So that's kind of our notation. We t in the subscript is our alpha over 2, and then our degrees of freedom comes right after that. Okay, so going back to the other situation where, say, we had a standard normal distribution. Does anyone remember what my critical value z sub 0.025 was? So if I want a 95% confidence interval, remember what that was? 1.96, exactly right. So you can see that there is a difference here, right? So before, if I assume that I know what the standard deviation sigma is, my critical value is 1.96. If I don't know what the standard deviation is and I need to estimate that, then my critical value is larger and my confidence interval will be bigger. So slightly changes what the answer will be because I'm estimating the standard deviation there as well as the mean. Yeah, Mary.
On the table, the top says alpha and alpha over 2. So if you look up 0.05 in this case?
Yes, good question. So the question was, the table, the top row says alpha instead of alpha over 2. So still look up 0.025 because, sorry, I'm having a lot of things around here. So if in here is 1 minus alpha, then I want alpha divided by 2 in each tail. So the table is giving you area to the right of something. So in general, that's denoted as alpha, but when you want an area of alpha over 2 in both tails, then the area when the total area of both tails, you want that to be alpha, the area to the right needs to be alpha over 2. So do make sure to look up alpha over 2 when you're doing a confidence interval like this. It's a great question. Yeah, Matt?
If you get more population, will the number be closer to that?
Exactly, yeah. So the question was, as your population, as your sample gets bigger, so n equals 5 here, as n gets bigger, will the number get closer to 1.96? Absolutely, yeah. And actually, if you trace down through that third column, the 0.025 column, you can see that number does indeed get closer and closer to 1.96 there. So as the population gets larger, again, remember we said the t distribution becomes closer and closer to a normal distribution, and therefore the critical value become closer and closer as well. Yeah, very good question. Okay. So that was addressing the issue of what happens if we don't know what sigma is. So kind of to review so far, our first motivating example was we have a normal population, sigma squared was known. Our confidence interval formula was that x bar plus or minus z sub alpha over 2 times sigma over the square root of n plus or minus that. So now we've addressed that first issue. We're saying we don't know what sigma squared is now. So our formula looks similar, right? It's still an estimate plus or minus something, margin of error. But there's two differences here, right? So now we have a t instead of a z, and I'm also estimating the standard deviation instead of assuming that I know what it is. Okay, so bottom line here is that our formula changes slightly. You need to adjust how you find your critical value, but otherwise the calculations are almost identical here. Okay, so that was addressing our first issue of we don't know what the standard deviation is. Second issue, we haven't talked about that, so let's say something about that quickly. So what if my underlying distribution now is not normal? So that was our other issue, where often we'll run into situations where the data is not necessarily normal. Okay, well, this is going to throw it back to Chapter 5 as well. So from Chapter 5, anybody remember what we did if the distribution was not normal? So yes, so we standardize, right? We subtract the mean, divide by the standard deviation. But if our population distribution was not normal, we could still calculate probabilities about the sample mean, right? So what was that main result that we used back in Chapter 5? Central limit theorem, exactly. So in Chapter 5 we saw the central limit theorem. Or the CLT. And what that said was that if n was bigger than 30, so that was kind of our cutoff point, as long as our sample size was at least 30, then x bar minus its mean divided by standard deviation of the square root of n was approximately distributed as something that was normal. So this is approximately okay. So even if my population is not normal, as long as my sample size was big enough, we had that this thing worked out. So that's some of the review questions. That's what we looked at back in Chapter 5. You know, what's the probability that the sample mean is, I don't know, bigger than 10 or less than 13? And we were able to standardize and use that Z table even if your population wasn't normal. So as long as the sample size is still big enough, we can still apply the central limit theorem. And what we'll have here is that x bar minus mu divided by s over the square root of n is going to be approximately distributed as a t. Still going to have approximately a t distribution with n minus 1 degrees of freedom. So even if this is true, even if the population distribution is not normal. So the good news is the formula is exactly the same. I just need to make sure that I have sample size that's big enough here. Okay, I think we're finally ready to do an example. Any questions or comments before we move on? Okay. So let's go ahead and look at an example. So we'll see this example a few more times, but let's think about a manufacturing example. So this company sells paper with 3 holes punched in them, sort of pre-punched in these, and we want the holes to be punched 8 millimeters from the edge of the paper, but again, it won't always be exactly 8 millimeters, right? There's vibrations and there's maybe error in the manufacturing process. That distance might be different. And so, kind of thinking about you're maybe a statistician hired on to determine if this machine is correctly doing the correct distance here for the hole punching. So what you might do is you might take a sample from 40 randomly selected drill batches and measure the distance from the edge of the paper to the hole, and find that the sample mean of this thing is the average distance from the edge of the paper to the hole is 8.0282 millimeters with a standard deviation of 0.0860 millimeters. So pretty small standard deviation there, but so what we want to do is we want to find a 90% confidence interval for sort of what is the true average distance there for this manufacturing process. So what's a 90% confidence interval for the population average distance that the holes are drilled from the edge of the paper? Okay, so question here. We want to find a 90% confidence interval. So let's write down what the setup here is. We want a 90% confidence interval for mu here, which here mu is the population average distance that these holes are punched in from the edge of the paper. Okay, so we need to figure out what what setting we're in here. So remember we've talked about sort of a few cases now. We have, if we know what sigma is, we have one formula. If we don't know what the population standard deviation is, we have a different formula. And if we have a normal distribution, we're good. If we don't, we need to make sure that we have a big enough sample. So this is kind of giving us this idea of checking conditions, or just figuring out kind of what boat I'm sitting in here. So as long as some conditions check out, I can use these formulas. So again, looking back at this example, do I know anything about the population standard deviation? So am I told anything about sort of the standard deviation of the manufacturing process? No, right? So I'm told a standard deviation, but this is from this random sample of 40 pages that I've selected here. So so I don't know what sigma is, but that's okay. We can deal with that. So we're going to use the t distribution because I don't know what sigma is. And do I have a normal distribution? Do I know anything about the distribution of the hole punching distances? No, I don't. So I also don't know the population distribution. But what's going to be kind of our out here? Why can we still sort of go ahead with using these formulas? Central limit theorem, exactly right. So sample size is 40. So n equals 40, which is most days anyways bigger than 30. So we can use the central limit theorem. That will help us. We can still use this formula even though we don't know that our population distribution is normal. And maybe I should have written this first, but in all of our statements, we've also wanted to make sure that we have a random sample. So even if it's not from a normal distribution, we do want to make sure that we have a random sample. And here we do indeed have a randomly selected. So we do have a random sample. So that's good. That's something else that we do need. Yes, sir.
Why do we not know sigma?
Why do we not know what sigma is? All right, so sigma is again, thinking about it's the population standard deviation. So sort of thinking about your individual random variable here in this case would be each sheet of paper has the holes are punched a certain distance from the edge of the page. Right, and so again, the idea here is that due to vibrations in the process or just general variability, that number is not always going to be the same, right? So that distance that it's punched from the edge of the paper is a random variable. Think about it that way. So you don't know how far it's going to be, but it's going to have certain properties. So it's going to have a mean and it's going to have a standard deviation. But as far as the population is concerned, we don't know what that is. So what I'm told here is I'm told information about my sample. So I take 40 sheets of paper out of this thing and I measure how far that hole is from the edge. And from those 40 numbers, I can calculate the sample mean. So that's 8 point. So here this is x bar. And this here, and then I can also calculate the standard deviation of those numbers. So this is my sample standard deviation S. So again, in general, you're not going to know to know what the population standard deviation is, we'd have to sample every single sheet of paper that came off of this process, and then calculate the standard deviation. So we're not going to do that, right? Then you'd have no papers left to sell. So in general, we don't know these characteristics about our population. So that's why we're estimating them here.
So we don't know the mean either then?
Exactly right. Yeah. So we don't We definitely don't know what mu is. If I know what mu is, then I'm done, right? So if I know the mean is actually 8.1 millimeters, then I'm done. Nothing to say else. Nothing else to say. So yes, so that's a great point. Maybe I probably haven't said that clearly enough. We're trying to estimate the population mean. We're trying to estimate our parameters, kind of like we were back in chapter 6. We're trying to use data to make a statement about something that we don't know, which is that population mean here. Very good question. Okay. Okay. So because I have my central limit theorem kicks in and I have a random sample, I can use that T formula. So we can use the formula for a confidence interval with the T distribution. Okay, so that's the most recent formula we've looked at here. Okay, so that means what I want to do here is, remember my formula is x bar plus or minus t. So in general it's sub alpha divided by 2 with n minus 1 degrees of freedom times the standard deviation s divided by the square root of n. Okay. So let's make a note of what. So we need 4 pieces of information here to calculate that. So we're told what our sample mean is. That was 8.0282. I also know what my sample standard deviation is. That's 0.0860. And I know what the sample size here, n, is. That's 40. So now I just need to find what that critical value is. And so what I need here, I need t, again, I want a 90% confidence interval. Therefore, alpha is going to be 10%, 0.1. So I need a t of sub 0.05 and 39 degrees of freedom. So now you'll go back to your table. And so what you would want to do is find the 39 degrees of freedom row. Does anybody see a 39 degrees of freedom row in there? Yeah, so 39 is not there, which might often be the case. So what we want to do is then you can round. You always want to round down, and that will kind of give you a more conservative interval. So round down to use the 38 degrees of freedom. So then instead of, again, the critical value that we want will be approximately equal to a t of 0.05 with 38 degrees of freedom. And what's that number going to be? 1.686. Thank you. Okay, so in the case that the degrees of freedom you're not looking for is not in the table, always want to round down. So even if you have, for example, 59 degrees of freedom, instead of rounding up like you normally would to 60, you round down to 50. So always round down. Yeah.
Why can't you just average like 40 and 38?
Why can't you just average 40 and 38? Well, it would also be approximately correct, but just for the purpose of using the table, let's stick with the numbers that are listed there. So yeah, if you took the average, that would probably be pretty close, but just go with the number that's in the table. Yeah. Okay, so now I have everything I need to calculate this interval. So my confidence interval is now 8.0282 plus or minus 1.686 times 0.0860 divided by the square root of 40. Calculate that out. That will be that will give me an interval of 8.0282 all the way up to, sorry, 8.0053 all the way up to 8.0511. Okay, so again, that's our calculation, but again, we are never done until we do what? What do I still need to do here with this interval? I need to interpret it. I need to say what this means here. So again, our usual interpretation is here is we are 90% confident. So I have a 90% confidence interval, so 90% confident. Again, that the true average distance that these holes are punched from the edge of the paper, so that true average distance is between 8.0053 millimeters and 8.0511 millimeters. And again, remember this true average distance. That's my population mean mu. So I'm just saying what mu is here in this case. Questions, comments? Okay. Well, I think this is a good place to stop. So thank you guys so much for being here. Have a good rest of the day, and we'll see you on Wednesday. Pardon? Oh, pretty well.